One of the really important concepts in physics and momentum is the concept of angular momentum, the momentum of spinning objects. So we make gyroscopes work, it's how you're able to ride a bike. But before we can talk about that, we first need to talk about angular motion. How do we describe objects that are spinning? So this should be fairly quick. All we need to do is define a few terms. So first of all, we need to have a way of talking about where an object is as it's rotating. Because if you imagine something like a disk, clearly it takes effort to turn the disk. But the center of mass of the disk hasn't actually moved. So the way we've been thinking about it before, just the center of mass of objects and just moving them in certain directions, that clearly isn't a valid way of thinking anymore. Instead, we have to define some direction for the disk. And we can do this arbitrarily. We can say it starts pointing up. And then we have to say that we rotate the disk. We rotate it through some angle. And this puts it at a new angle, and we call this angle theta. And that's the Greek symbol for theta. It means angle. And we use this to measure the angle of something, and we measure it in radian. And 2 pi radians means 1 full circle. So if you say that theta equals pi radians, that means it's rotated 180 degrees from whatever the 0 position is. And this really isn't that complicated. We just define a system of measurement, and we use that from now on. So now that we have a way of describing what angle it is, we just say theta, and we define the angle in terms of radians, with 2 pi being a complete circle. Now we're ready to move on to angular velocity. And angular velocity is omega. And I know that it looks like a W, but it's really not. It's actually the Greek letter omega. It's the last letter in the alphabet. It's the one we use to talk about angular velocity. And angular velocity is just position divided by time, very similarly to normal velocity. Except in this case, position is theta rather than an x or y coordinate. So as a result, it's theta over time. Theta is measured in radians. Time is measured in seconds. So it's radians per second. And if you have an object that's spinning at, we'll say, 1 radian per second, that means in the first second, it makes it a full radian. So if it's going at pi radians per second, that's an important distinction. It goes a full pi in the first second, and then a full pi in the second second. So in 2 seconds, it's got a complete rotation. If you're going at 2 pi radians per minute, then in 1 minute, you make a complete revolution, and you're going at 1 RPM. So you can convert back and forth between all of these systems of measurement, but the important thing is we just talk about this angular velocity, how fast something's spinning. And we now have position, which is roughly equivalent to x or y position. A lot of the same rules apply, except for the fact it's not translating, it's not sliding. Instead, it's rotating. Then we have omega, which is angular velocity, which is the same idea as regular velocity, except for the fact that it is in rotation once again. But now we need something to correlate to acceleration. And we don't have anything to do this job. So we create an angular acceleration. An angular acceleration, represented by the Greek character alpha, is how fast it's accelerating. And just like angular velocity, we can use a lot of the same equations. So it's omega over time. And that's in radians per second divided by seconds. So radians per second squared. Now, just like Newton's second law, every action is an equal and opposite reaction. How that creates accelerations with equal and opposite accelerations. We also have equal and opposite angular accelerations. For instance, if you want to spin a top, you'll notice that you have to twist your hand and you apply force, and something pushes back on your hand in the opposite direction. Or if you want to rotate a merry-go-round, it's going like this and you're trying to spin it. You push it that way, it pushes you back in the opposite direction. And if you kept pushing on it, it would keep pushing back in the opposite direction as you did a complete circle. And as a result, it'd be giving you an angular acceleration and eventually an angular velocity. Because of this, we can talk about angular momentum. Now, the one wrinkle here is, whereas with regular momentum, we can say momentum equals mass times velocity. We can't say that angular momentum, which is expressed as L, is mass times angular velocity. And the reason for this is when something's at an axis, if it's near the end, it has a much higher velocity and has a much higher momentum than something nearer to the middle, which should have a lower momentum. So as a result, we need to take distance into account somehow. And for our purposes, we say that distance is radius squared or length squared. So we say that angular momentum equals mass times radius squared times angular velocity. And this equation is going to be very important later on. And next lecture, we'll learn how to calculate moment of inertia for different shapes and solids that aren't just single points rotating around an axis.